we can move to the next and last, if I'm not wrong, talk for the session, which is from Imants Pulkstenis from Eventech.
Yes, that's correct. Do you hear me?
Yes, it's a novel correlation LIDAR sensor for Earth observation and resources management. Yes, we can also see the
presentation also is seen. Yes.
Yes. Yes. Thank you.
Okay. My name is Imants Pulkstenis. I'm an engineer in company Eventech, and today I will present you our study results regarding correlation wind LIDAR and imaging LIDAR system that was performed with our partners in United Kingdom. In this study, we have two main goals that exploit same core principle. The first goal is to demonstrate that imaging LIDAR system can be functionally optimized with advantage timers to get higher image range and contrast performance with potentially lower resource requirements. The second goal is of the project is to create a wind sensor concept that will give new or improved measurement capabilities with potential space operations in upcoming space missions. Study team consists of two main partners, each team with extensive scientific background in their fields. And each team member was responsible for separate activities. Our partner Paradigm Factor from United Kingdom was responsible for imaging LIDAR system and correlation wind LIDARs. They performed a high number of experiments at their facility and achieved very remarkable results. From our side, our stronger side is electronics and time measuring devices. We have more than 40 years of studying high performance and high accuracy event time measurement system. And one of our colleagues, Dr. Bezpajko, was mentioned in previous presentation. It is first very surprising and very pleasant surprise. So in this study, we also used our timers to improve imaging quality. If we talk about imaging LIDAR system, it exploits through 2D photon counting detectors with high resolution timing for each photon event. Those images are then post-processed in PC, and we can obtain 3D field. If used from space-based system, those 3D images could be used to study topography, forest, ice, snow, water surface distribution, and other fields. Imaging LIDAR system, we used ultraviolet laser, which illuminates target and then polarized beam splitter with quarter-wave plate used to ensure high efficiency of transmission and reception of LIDAR signal. Then we gather backscattered signal from the target region, and it is passed to photodetector. Laser pulse is 350 picosecond duration, and it is synchronized with all data acquisition chain. Then our time tagging detection system ensures and captures every data and sends to PC to later analysis. The compact LIDAR system has been demonstrated to be capable of target detection and identification far beyond the limits of standard capabilities of eye or camera. Especially under conditions where visibility is highly challenged by fog or clouds. The LIDAR employs near ultraviolet laser, 355 nanometers wavelength, with short duration pulse as a source. If we talk about correlation wind LIDAR, the LIDAR system use the same laser and operates in the same 355 nanometers. That allows us to obtain high resolution spectral saturation that we can isolate the MIA signal from aerosol and usually larger Rayleigh signal from molecule scattering. And those signals can be then filtered and passed to the processing unit. In those pictures, you can see the ground test system. The correlation wind LIDAR is a second wind system in operation in Paradigm Factor facilities in UK. It sweeps around all 360 degrees azimuth around 30 seconds and detects the aerosol patterns in the sky, in the field of view, and this gives the system a new image of the sky every half minute. And those images represent the change in aerosol features that move into our field of view, and later analysis of this movement allow us to calculate the wind speed. The correlation wind LIDAR is mounted on the, as I mentioned, the scanning axis. It is shown in top picture. We also installed all-weather proof dome, which can transmit UV wavelength light, and this allows us to gather data almost in any weather conditions. In a lower figure, you can see the 3D image of 5 consecutive scans of the atmosphere, what is obtained by correlation wind LIDAR system. Initial tests to obtain wind field from correlation measurements have been performed with MATLAB normalized 2D cross correlation function. It is hard to see, but in principle, there is a star. You can see pointer. I have pointer. Yes, I have pointer. So there is a star, and we cross correlate this region with the next picture, next scan, and try to determine what are the feature movements. So yes, in this slide is presented how the cross correlation works in the ground-based system. Auto and cross correlation is applied to collected data that is provided by the movement of aerosol features, and those features, movement to those features allow us to estimate the motion of the wind. Of course, there is a limitation. If movement of the features is too fast, the feature moves out the side of view, and we cannot calculate the wind. But before that, we need to pre-process the data. This is very time-consuming task. It consists of gathering data from all systems. It is a large amount. Summing, averaging photons from each scan, multiplication by the distance square, background noise calculation and subtraction, and then those summed and corrected data is passed to MATLAB DSP package, and we can determine the wind vectors. This picture shows the magnitude of correlation coefficients, what is a blue curve, and corresponding LIDAR profile, red curve. it can be seen that the max correlation coefficient follows exactly the LIDAR profile. After initial saturation, the correlation coefficient drops and then rises again in correspondence to the probably light, not visible cloud or urban aerosol coming from the London. So in this slide, we can see same data as a point of cloud image, and we can see that it can be seen visually that there is some cloud aerosols. It is a dry and clean weather conditions during May of 2020 in Park Cottage location of LIDAR station West Sussex, south of London. There was good visibility conditions, and this is a real rural area, and there is very low noise. Only noise comes from London. So cross correlation allows us to calculate wind magnitude, and the left picture are corresponding atmosphere point cloud. So we can see that we can cross correlate those images, and with cross correlation algorithm calculate the wind vector. To further understand the nature of scattering aerosol at low altitudes and its relative azimuth in invariance and empirical methodology has been developed, and it's been used to understand relative role of aerosol and molecule scattering and extinction at the lower ranges. Figures in the slide shows the calculated backscattering and extinction coefficients for one of our test results. If we talk about more about our Eventec technology, this is the initial timer what was used in experiments. This is most popular our device. Its key characteristics is 2.53 picoseconds single shot precision, but main limitation is only 2 input channels. To match multi-channel input from photon detector, we need to develop at the start the serializer delay line unit that can be used to serialize captured LIDAR data to the event timer. Later in the project, we designed a new hardware with much lower resolution, but with this resolution sacrifice, we can get multi-channel functionality. And this hardware was used in all latest experiments to capture data. From the PC side, we used USB 3 interface, and its speed was enough to ensure that all laser data was captured and not missed due to memory overflow. If we talk about future plans, newly designed prototype will act as fully automated wind processor input device. The overall study has established the validity and viability of applying correlation technique to 2D image to determine the atmospheric wind vectors. It has been found that pre-processing and processing of LIDAR data require several time-consuming operations, which is done mainly manually, and development of specific data processor and the wind LIDAR processor will greatly enhance the possibilities for wind and other imaging processing of such sensor. Currently, we are developing this processor as a study contract from ESA, and main focus is the wind correlation processor. study is in early stages, but we are hoping that it will be very successful and will lead to new instrument for study. As I already mentioned, the study team consists of two main partners, that is Eventec from Latvia. We have also Dr. Armandillo, optical advisor, and the study was partially funded by European Space Agency as a part of PEX framework. So this is all for me.
Thanks a lot for your presentation. There are two questions, immediate questions. I think the first was from Rees from Imants.
Now, it is a very interesting wavelength region in which you have 355 nanometers. It is quite short waves on border between violet and ultraviolet. Atmospheric aerosols are of similar order of magnitude. Their particles, they can be larger, they can be smaller. And my question is, when you interpret scattering in the atmosphere on aerosols and also relay scattering, do you interpret it as multiple scattering or single scattering approximation? And do you account for polarization?
I'm sorry, I will not be able to answer, but I see that my colleague Eriko is.
Yes.
Yes, Eriko, please answer.
Yes, I can. Yeah. The geometry. Hello, good morning, everybody, or good afternoon in Riga. The geometry there from ground. Essentially, the field of view would not allow at the distance we operate. Essentially. Multiple or the difference between a single and multiple scattering. What we get overall scattering within the field of view. But the interesting thing is that for space, there would be no, due to the distance, there would be no much of a concern of issue multiple scattering. Because again, we will have relatively short field of view, not a small field of view. In terms of the impact of aerosol and the molecules with respect to wavelength that you addressed at the beginning, we have, in principle, if we operate in UV, we need to filter out molecular scattering, which could be quite intense in UV. The reason that we use UV, because we have on site a similar system, but it's a Doppler wind, which we utilize for the calibration validation of ion satellite. I would like to recall the audience that this project, partially funded by European Space Agency, is foreseen as a future evolution of alternative 12 satellite, which is Doppler wind. Okay, so that's why we operated UV, but a much better configuration would be to operate in the visible or infrared, because aerosol, which is responsible for our signal, is not being much affected by changing wavelength. It's quite constant. So what we have on the ground system, we have a filter. We have a new filter which we did not implement, and that's why we see that in the first layer we have a clean atmosphere. The molecular scattering can be quite strong in UV, and that's why we have been doing calculation actually from. We have been resolving the LIDAR equation based on actual experimental data. And in fact, we see, if you look again at the data of aerosol, the molecular scattering, that in the first layer, a molecular scattering might be quite strong, which is responsible of the saturation and of the independence of range in the first 100 meters from the ground. So essentially, the first 100 meters, we have strong molecular scattering. So above that, aerosols start to dominate, and then we see clearly the fissure. So I don't know if this, maybe I got a bit overextended in the explanation, but I hope this answered some of your questions.
Well, thank you.
You're welcome.
Next question from Vladislav.
Oh, thank you for your talk. It's again, I see merge of technologies like LIDAR and precise lasers, and I understand it will be mounted on satellites. And first question, how big it is? So it's definitely not CubeSats. And second question, what heights are you targeted to test winds? As I understand from air tests, it's around 1,000 meters. But if you're looking for satellite, probably you are targeted for troposphere winds. So what kind of heights you're looking for?
Our goal is to develop system that will be mounted essentially in satellites, and we are looking to develop system that will be small enough and energy efficient enough to be deployed in small sat constellations. That's why this system is more like, if compared to Doppler system, it is more energy efficient in the laser terms. So all this processing is done on PC side and the microcontroller side, FPGA side, and lower energy in the laser is needed. So focus is to develop small sat system. Now, currently, we are testing and developing this technology on the ground, of course. And for heights, this system works only on aerosol scattering. So the height is 1,000 kilometers, if I remember correctly. And any other winds will be not detected. But this is a topic for our partner from UK, David Rees. If you are interested, we can talk and meet together and discuss this topic. He's our top meteorologist and LIDAR specialist.
Yeah, thanks a lot, because we are also interested in our university in wind studies, but we do it from air and interested in hundreds meters, maybe 500 meters. But to make a proper models, we need also proper data from heights about several hundreds of kilometers as well. So probably we can find some cooperation in this question as well.
Yes.
Thank you a lot.
Okay, maybe can I add something to your question about altitude? I should point out that, as a matter of fact, we are limited by the SNR, the ground system we choose, and I should point out that we only use 20 microjoule energy, which corresponds to 20 milliwatt average power. So we have extremely energy efficient system. And as a matter of fact, it is the photon counting which ensures us very high detection efficiency. Now, despite we have so low energy, we can reach reasonable SNR with the integration of 1,000 pulses, because we operate the system at 1 kilohertz. So we integrate 1,000 pulses in 1 second, we can reach up to about 4 to 5 kilometers. Okay? Now, we have done simulation, and we expect that the system for space, at the moment we have 20 milliwatts from ground, but the space system, alternative to the present EOLUS, or 1 watt, which is 1/10 of what at the moment is used, could be measuring aerosol wind up to troposphere. As Imants mentioned, we are also studying, exploring now alternative, much compact system applicable for CubeSat or for small satellite constellation, where we use a much more efficient laser technology. At the moment, we use a YAG, harmonic YAG, but we'll be using in the future effort, which we are undertaking, now we'll be using either fiber laser from communication technology, which has much less average power than EOLUS, or we will use what is emerging now, microchip laser technology, which is having a big impact, which is a kind of variation of YAG, but it's a microchip package equivalent to several average power of what with 100 picosecond pulses. So we have room for major improvement either for space or either for small sat, CubeSat application of environmental, wind, and this land observation. I hope that was a bit clearer on the prospect of this technology. And certainly, with Deventech, we are very much open potential cooperation for application wind and related wind technology with this very small compact system that we have been developing and we will continue to develop. Thank you.
Thanks a lot. As I understand correctly, direct measurements in troposphere winds are currently very difficult and very rare, and your system can be multiplied in hundreds of satellites.
Exactly. That's the idea. And how do we achieve that? Because we are not magicians. How do we achieve that? We achieve that thanks to a photon counting, single photon counting, thanks to the correlation, efficient cross-correlation technique, and with a new laser technology, with advanced laser technology. The technology which is being used by EOLUS, which is the current LIDAR system, wind system we have in space, is a 40-year-old technology. Okay? The meantime, progress has been huge. As I said, we have fiber communication technology which ensure power of the order of several hundred milliwatt. We have at the moment, from ground 20 milliwatt, but we can have a few hundred milliwatt from a CubeSat application, 200, 300 kilometers. I mean, that should be okay. And we have this new high resolution Eventech technology on photon counting, which is really state of the art. So combination of advanced receiver technology, photon counting, and processing, and advanced laser technology make today possible to develop a system much smaller, much more energy efficient, and for a multitude of application, wind, but not only wind, for space and also from airborne or small satellite constellation. Maybe offline we can discuss potential cooperation to this if you're interested in.
I think we will be very interested in discuss this question maybe after conference. So I know Eventech colleagues, so we definitely come to you to your promises and discuss these questions.
Yeah, we'll be glad of that. Yeah. Thank you very much for your interest. Yeah. Thank you.
Thank you a lot.